We're now going to be using our knowledge of vectors to treat a pretty common situation, and that's the case of projectiles moving through the air. So projectiles will have both horizontal and vertical motion, so we might be interested in separating those components out. It turns out that what happens in the x direction doesn't really matter for what happens in the y direction for these projectiles. So, instead of worrying about solving everything at once in 2 dimensions, we could really treat a 2-dimensional problem as like 2 separate 1-dimensional problems. So let's look at a case where we have, say, a long flat piece of ground and a ball, maybe a soccer ball, that's going to get kicked upward from the ground, and we'll say it's kicked upward at 30 degrees, and how about at 25 meters per second, so really giving a heck of a kick. So we can kind of just guess on the path of this ball. Then it's going to be this curve back down to the earth. So while it's in flight, we can use those kinematics equations to model its motion. So first thing we need to do is break up what we have into x and y pieces. You might find it useful just to kind of make a table of x values and y values, and keep track of things that way. So things that we might be concerned with would be the initial position and the final position, the initial velocity and the final velocity, and the acceleration, and then the amount of time that goes by. Now that doesn't really get put into x or y direction individually. That's going to be something that's common to both. So these variables then are going to be what we're concerned about for this. And then we have a couple equations that we can use for these problems as well. So we've got the position function. This could be x or y, it doesn't matter. We just need to change all the x's to y's if we want to do it in the other direction. X is equal to the starting position plus the starting velocity, and I'll just make a note that that's in the x direction, times time plus 1/2 ax times time squared. Velocity at any moment in time is equal to the starting velocity plus the acceleration times the time. And if we wanted to go x direction, we could just add some x subscripts there. We could also do the y direction with these same things. So let's look at our problem and see what we know in this. Well, basically all we need to know here is values for acceleration and for our initial values for position and for velocity in the x and the y direction. We don't need to know a time here, because this one we're just being asked to write write expressions as functions of time. That just means we're going to leave t in there so that later on someone could say, okay, I wonder where it is at a time of 3 seconds, and then they have the expression that we've written. They can plug in 3 for t and get an answer for where it is or how fast it's moving in the x or in the y direction. So what we know for initial, well, the ball starts on the ground and starts right here. It makes sense just to say, we'll call that 0, 0 for its initial position. We don't know exactly where it's going to end, but I can see it's going to be back on the ground. So we could put down that y would be 0 at the end. But again, we aren't going to make the assumption that somebody's looking for where it is at the very end of this. We want to keep it open. So where is it at any time along its path, or how fast is it moving at any time along its path? So we'll stick just with the initial information there for position. We need to do the same thing for the initial velocity for these. So we've got that 25 meters per second at 30 degrees. So we need to split that up into the x piece like this and the y piece. And so the y piece there is going to be 25 times the sine of 30, which would just be 12.5 meters per second. And then the x piece will be the 25 times the cosine of 30 degrees, which is 21.7 meters per second, and those values can go in here. 21.7 meters per second and 12.5 meters per second. Okay, and then the only other thing that appears in these equations that we need to get rid of is acceleration. Not get rid of, but put a number in for. So, in these problems with projectiles, right now anyway, we're going to assume that there's no air resistance, and so a projectile, as it's flying, it's only acted on by gravity. And gravity pulls it downward, it makes it accelerate downward, and it turns out the rate that it makes it accelerate downward at is 9.8 meters per second squared. So if we drop something from rest, after 1 second it'll be going down at 9.8 meters per second. After 2 seconds it'll be going down at twice that, 19.6 meters per second, and so on. So 9.8 meters per second squared, and it's downward, so I gave it a negative sign. Gravity doesn't pull anything left or right, and we said that's the only thing that's changing the object's motion as it's flying, so acceleration in the x is just going to be 0. So now we can write equations for the position and the velocity as functions of time. So x is going to be, x naught is just 0, plus v naught, 21.7 meters per second, times t, plus 1/2 times 0. So the position, we see 21.7 meters per second times t. That's just a linear relationship between x and t. So when we graph that, that'll just be a straight line. So let's go ahead and do that. So x versus t, at a time of 0, we'd be at a position of 0, and that fits with what we defined the initial position to be. And then from there on out, it's going to be a line that's got a positive slope, and a slope of 21.7 in this case. So a linear graph for position versus time there. How about the velocity versus time? We'll do the x direction still. So the velocity in the x direction is going to be the starting velocity in the x direction, 21.7 meters per second. Starting velocity in the x, plus acceleration in the x times time, but acceleration in the x is just 0. So that's plus 0, and velocity in the x is just 21.7 meters per second. So now if we graph that quantity, we've got just a, let's see, so this is velocity x, and this is time. Now we've got just a constant value, straight line at a position of 21.7 meters per second. There, okay. So that's the x direction. The x position is going to be a linear graph with a positive slope in this case. It could be a negative slope if it's moving the other direction. But in the x direction, these always end up being positive because acceleration is always going to be 0. Or, sorry, these not always positive, but always linear, because the acceleration is 0. And then here, same deal, because acceleration is 0, velocity is not going to change, so we'll always see a horizontal line for this graph. Alright, now y direction is a little more interesting. So we do the y position as a function of time. Just use this equation, but substitute in y's instead of x's. So y naught is 0, plus the initial velocity in the y is 12.5 times time, plus 1/2 times the acceleration in the y is negative 9.8 meters per second squared, times t squared. So y is going to be 12.5 meters per second times t minus 4.9 meters per second squared times t squared. Oops. Okay, so our graph of y position versus time is going to be, well, it's a quadratic. And we have this, the squared term has a negative coefficient, so we know it's going to be concave downward. We know it starts at a position of 0, and so it's going to be, something like this. Quadratic function there, or a parabola shape. And I messed up here. This should be a time, not another y. There we go. Okay, and then looks like we're out of space here. Let me clear a little room. Get out of here, velocity in the x. Let's do velocity in the y. So velocity in the y, that's starting velocity in the y, 12.5, plus acceleration in the y is negative 9.8 meters per second squared times t. Okay, so this one is another linear relationship, so we'll have a straight line for our graph. But this one will look a little bit different. So we see after 1 second, the velocity in the y direction is going to be down to 2.7 meters per second, so 12.5 minus 9.8 times 1. After 2 seconds, this negative 9.8 times 2, that's negative 19.6. That's has a greater magnitude than the 12.5, so our velocity is actually going to go negative in this case. And so it turns out that this graph is going to start out at some positive position, 12.5 meters per second up here. And then from there it's going to be traveling downward, and it'll be a straight line with a negative slope because of this negative 9.8 meters per second squared. So the see the velocity for the x I got rid of, but position for the x is a straight line with a positive slope if we have a positive starting velocity, or a negative slope if we have a negative starting velocity. The velocity in the x direction is just a constant value, so it's that horizontal line. The position in the y direction is a parabola. We can tell whether it's concave up or down by looking at the coefficient on the t squared term. Positive coefficients give us concave up. That's one that looks like this. Negative coefficients give us concave down. That looks like this. So this one is a negative 4.9, so we get a concave down one. And then last up, our y velocity as a function of time is going to be another straight line. It may not start at 0, and that's fine, but it's going to be a straight line with a positive slope if the acceleration is positive, or a negative slope if the acceleration is negative, like this one is.